Okay. So you got back your test, and again, just so you know, the next test, don't expect it back the next day. This one here, the material's easy. And that I also had some free time to just happen to fall on my lap, so I made good use of it. This is the easiest test we've had. The material is getting where we get significantly more abstract and harder. So things are going to be, enjoy the test while you have. Okay, so okay, let's start. So we have all the postulates of quantum mechanics. And what I want to do now is I'm going to do something that is not in I gave you this handout here of the Schrodinger equation. I'm going to go do something which is normally not done in modern. I want to go over it because basically I don't know really how to do quantum mechanics without these things. And so it's going to be a more subtle point, and it's important. So all the operators. All the operators in the second postulate, okay, are Hermitian operators. And that turns out to be really, really important. What I want to do is talk about what it means to be a Hermitian operator. Okay. Any operator that is Hermitian obeys the following. That is, let's say has the obeys is the following property. Okay, it's going to be this. That if we integrate over all space of f star O acting on G, now explain what f and G are in a second, dx, that equals this. The operator acting in f plus G dx, where f and G are arbitrary functions. Is Hermitian. So the L here, if I put in the px operator, the px operator obeys. If I put in the energy operator, the E operator here, I'd have to change my X to a T, but again, it would obey this here. Okay, it's going to obey these properties. And you could say, well, okay, well, that's well and good. I'm glad it's Hermitian. Well, it turns out that if something's Hermitian, you get three very fundamental properties. Okay. Any operator that is Hermitian has three fundamental, three important properties. Okay, the first one. The eigenvalues of a Hermitian operator are real. That's really good because what did we say about the measured properties? The measured properties of a system are the what? Remember the fourth postulate? You measure a wave function. What does that wave function do? Collapses into the eigenfunctions of that operator. And the value you measure are the eigenvalues of that operator. Well, if you measure something, what it better be in a lab? It better be a real number. You know, you're not going to measure something it's not going to be a complex value. If it is, Nobel Prize that year. Okay, you're going to measure a real property in the lab. So that's good. The eigenvalues are real. Second, the eigenfunctions of a Hermitian operator are applied. Okay, I'll explain what that means in a second. Right now, just write it down. Don't worry about what the word means. Okay. Don't worry about what the next word means. I'm going to explain it in a second as well. 3. The eigenfunctions of a Hermitian operator form a basis. Okay, again, you may not have the word basis yet. I'm going to explain what the word basis means. Okay, just so you know, this is so essential that I'm going to ask you this on the next test. So the next test, you already know 2 questions. What 2 questions do I ask you on the next test? The first question is going to be what? Postulates. So postulates in detail of quantum mechanics. And then somewhere on there, I'm going to basically have you, using this definition, prove these properties of a Hermitian operator. Why? And if you take the course actually next spring, when I'm teaching quantum mechanics, I'm going to be doing the exact same thing, having the same functions. This is something you can't do quantum mechanics without this. Okay? And so most books, when they start off with, like in modern, when they start off with quantum mechanics, they don't go into this detail. In my mind, you can't do anything without this. And so this is what I'm doing. So what I want to do is prove each of these properties, and then I'll explain what this means and what this means here. Okay. So proof of these 3 properties. Okay. 1, the eigenvalues are real. Okay, so what does this mean? This means if O acts on some eigenvalue here, on some eigenfunction here, I'm going to call this phi n. So I'm going to let phi n be the nth eigenfunction of O. So it turns out when you solve for these eigenfunctions, you're going to get a lot of them. There's going to be a lot of these eigenfunctions. So this is going to be the nth one here. So when O acts on here, I'm going to call this lambda n phi n. So let this where lambda n is the eigenvalue, is the nth. Well, I'll just say is the eigenvalue or eigenfunction phi n. Okay. Usually the eigenvalues are usually denoted by lambda. So let's do the proof. The proof is quick. Okay. So what we're going to do is we're going to recall what's the definition of Hermitian. I deliberately erased it. Try to look at without looking at your notes. Remember it. I'll give you a hint. There's an equal sign.
What's the equal
We have the center overall space
of F star of
F star, where F is a
arbitrary function,
function.
and the operator,
The operator here, then acts on
and then GDX.
G, where G is a arbitrary function, dx. If this equals
And that equals the integral overall space
integral overall space,
of F and O with the star.
so O acting on F. It has to act on something, so it's going to act on F, and then we take a complex conjugate of all that
And then the GDX.
times G dx. So again, I'm going to erase it every time and then put it back in so you'll be forced to remember it. But that's about it. Thanks, Michelle. The only way you brains work is you have to kind of keep on getting exposed to the same thing. Okay, so we're going to let F equal G equal phi sub n. Now it's an arbitrary function, so I can let it equal anything I want. So if I put this in here, what do I get? phi n star, O acting on, yeah. It's a technical name for phi n. It's a joke. X equals. O acting on phi n, complex conjugate of this whole thing, phi n dx. Okay. You finish off the proof. We're basically done. What happens with O acts on phi n? What do we say phi n is?
The short.
No? Sure. It's an eigenfunction of O. What does it mean to be an eigenfunction? When this operator acts on here, if there's an eigenfunction,
Value. Same.
if the function back times
A constant.
a constant, and that constant is called the eigenvector. This is equal to lambda n phi n. And what happens over here? Hey, here I have it. Oh, it's acting on phi n. What is that equal to? Lambda n phi n. Hey, but what else are we doing to this weird thing? They're taking the complex conjugate of that whole thing here. Which equals what? This equals then lambda n star phi n star. Okay. So now let's put this all together. So put this in here. I get phi n star times lambda n phi equals again the OX on phi n giving me lambda n phi n, take the complex conjugate, so this whole thing here becomes lambda n star phi n star. It's phi n dx. Okay. What can I pull out of each integral?
All the lambda and star phi n out.
Yeah, the constant out. All right, this is a constant, this is a constant, so I can pull those out. So this is lambda n. Goes minus in infinity to infinity, phi n star, phi n dx. And that equals. Lambda n star, minus infinity to infinity, phi n star, phi n dx. Okay, what happens to those integrals?
They put a 1.
They might, they're going to, but we don't know that. But we don't need that, but they are going to be the same, so what do? They cancel, they're not zero. This is lambda n equals lambda n star. Okay, what is a number equal to its complex conjugate? Again, what does it mean to take a complex conjugate of something?
You just flip the sign of the I.
You take your I and you make it a minus I. So when does a number equal its complex conjugate?
If it's real.
Only if it's real. This right here, this is only true if lambda n is real. Okay. So therefore, the eigenvalues are real. Other information on it. Operator. Are real. Again, that's important because that's what we measure in a lab. So our laboratory values better be real. If you're doing any summer research with any of faculty members at Alfred this summer, they'll say, I measured the following complex quantity in the lab. They'll just go, oh, how long does summer last? Questions to that?
It's the phi n that you put in there is not the. Oh, it's psi. It's the
Correct.
Yeah.
I'm just saying it's an eigenfunction of O. It might be psi. Don't know, it doesn't matter what it is. It's just some random eigenfunction.
Gotcha.
Okay. Again, if our over the Hamiltonian, then that is then our eigenfunction is going to be the psi. But we don't know that yet. Although we're going to find it out later on today. Again, not a good day. Students. Okay, property 2. Prove that the eigenfunctions of O are orthogonal. I'm going to explain what orthogonal means, and then I'm going to give you the definition, and then I'll go from there. Okay. Two functions. Okay, if the functions, the eigenfunctions of an operator are considered orthogonal if the integral over all space of phi n star phi m, okay, dx equals 0 when n does not equal n. So basically what I'm doing here, I'm taking two different eigenfunctions, I'm taking the complex conjugate of one of them, and I'm integrating this mess over all space. Okay. These are not the same eigenfunction, this equals 0. This is the definition of orthogonality. Okay. Those of you being seeing this for the first time, it's only your introduction. You're going to see this for the rest of your life, assuming you continue to be in the field you're going to. This is something you're going to use every single day. In fact, it's lot to see. This is our students put this up a little while ago. They put up this, but I don't want to refer to that. Here's the comic here. Okay, then somebody hears, muscled out. Physics undergraduate. Hey, how did you get that way? And then it's in very bad print, they modify this. It says, every time I use orthogonality rules to do an integral, I did one push-up. Okay, that's going to be the orthogonality. And that's why you study physics, to be able to understand jokes on it. Okay. That's the only reason why you study. No other reason. So let's go through and do that proof. Okay, if you don't make use of this rule here, you will spend hours doing homework. Hours were something you could actually just look at it and then immediately write down the answer. And I mean, this is how much this is going to save you. This is going to be remarkable what you can do with this. And usually people come in and show me all this. I don't know how to do this integral. It's 0. How come? Orthogonality. Oh. Proof. Let's stay here. Proof. Let phi n and phi m be two different eigenfunctions of Hermitian operator O. With distinct. What does distinct mean? Different. Yeah, different. Eigenvalues. Lambda n and lambda m. Okay. I don't have to make the assumption of them being distinct, but then there's a whole other step in the argument that I don't want to get into. And I'm already kind of pushing the edge of modern physics. So I don't want to necessarily tell it break it. It's already getting expanded. Okay, so what this means here is what? This means when O acts on phi n equals lambda n phi n. That's what that one means. then that means when O acts on phi m, you get lambda m phi n. We're going to assume lambda n does not equal lambda m. Again, you don't have to make that assumption. It's true even if they were the same, as long as they're distinct eigenfunctions. But I don't want to get into that. Okay. You tell me where to start the proof. You don't need me. They could say, you know, test two. Here it is. Prove it. The class would be, ha! Ask us something complicated. You insult us with your puny question.
Do the integral.
Yes, we start with the integral. I'll give you the hint. The integral involves an equal sign.
You go from negative infinity to positive infinity.
All right, keep going.
I don't remember what the name of that.
We'll call it F.
Whatever it's called. Sure.
Star. O. G. Yes. Equals. Integral here of O acting on F. Complex conjugate of that whole combination. G. Yes. Okay. Okay, we're gonna let F equal something, and we're gonna let G equal something. Hey, what do you think we're gonna let F equal? What do you think we're gonna let G?
And fine.
One will be phi n, the other one will be phi m. Let's put them in here. Take good notes. I can't wait to find out what we're gonna get. I've always wanted to keep this close. Okay, phi n star. Oh, acting on phi m dx equals the integral from minus infinity to infinity of O acting on phi n complex conjugate phi m dx. Am I off the phantom zone? I am not. Okay. I don't want to run into general Zod. I'm kind of tired from getting those exams. Proceed. Yes.
Is there any reason why you put the O in front of the F for the second integral?
Here?
Yeah.
Because that's the definition. That is the definition of what it means to be a regression.
Because it's like
Now it turns out that there's another way of looking at these involving matrices that I don't want to get into. You take the course of quantum mechanics. It turns out there's different ways of doing quantum mechanics. We're doing everything in modern physics in terms of differential operators. It turns out you can redo everything in terms of matrices. And then that'll be a big part of quantum class. Basically finding out how to extend this into matrices. And then in which case, okay, don't worry about this. But in that case here, if this is a matrix, it turns out if you take the transpose of the matrix, followed by the complex conjugate of it, this combination here we call a dagger. And this one dagger. That's the case in this remission. And then this, I can then connect it back to this a little bit easier. Don't worry about what that means. It is called so the reason why people don't understand Macbeth is they don't realize that it's actually preparing you to understand quantum mechanics. And she says, "Is this your dagger I see before me?" She's basically contemplating the existence of quantum mechanics and how our classical worldview is going to be modified by basically the introduction of basically quantities acting on wave functions and the collapse of the wave function. It's a metaphor, and no one understood. You know, Shakespeare, he was so ahead of his time. Okay, proceed.
O m equals to like gonna be lambda m
Lambda m phi m. Hey, do we have another one we can do?
yes the other side
Hey, what's this?
lambda n phi n.
Lambda n phi n, and we're taking the complex conjugate of this, which is lambda n star phi n star. But do we know anything about lambda n star? I think we had a proof one.
Yeah, is equals to lambda.
These have to be real, so this is real lambda n. phi n star. So let's put this all together so we get. Okay, so what happens here is that we get them this integral from minus infinity to infinity, the phi n star lambda n phi m dx. And that has to equal then the integral from minus infinity to infinity of lambda n phi n star phi m dx. Okay, I can take out the lambda m's. The lambdas because they're constant. Then we have to be a little careful mathematically. Now, what's the tempting wrong thing to do?
Cancel the
Just cancel.
integrals.
You can cancel the integrals. Okay, then what we have, that give us a lambda m equals lambda n. But what did we assume about lambda m and the lambda n?
They're not equal.
They don't equal each other. So resolve the contradiction. Why can't you divide through by those integrals? When can you can always divide both sides by the same thing with one exception.
Yeah.
Hmm.
I don't know.
When can't you divide?
That
By
was
zero.
equal.
You can't divide by zero. Now, we don't know that yet, so let me go through and actually convince you that the integral has to be zero. That's why you can't divide them, because you divide by zero. That's why you get the contradiction. Well, let me show you the way that avoids this so you can see it. I can take this to the other side. If I take this to the other side, what do I get? I get lambda m times this integral stuff dx minus lambda n times this integral stuff dx equals 0. I can pull out that integral because it's the same integral.
Is it the same?
Yes. This is the exact same thing. This is. Okay. What do you know about this combination here? Lambda m and lambda n are. And they're different. So this does not equal 0. Therefore, this integral must
Equals.
equal 0. And that proves we're not bad. Again, once we actually start doing examples of this with the real problem, this will drive everything home and make it a little more concrete. This is also quite abstract. So this is eigenfunctions of Hermitian operator O or orthogonal. And this right here is called orthogonal. Okay. Now the next one I'm going to do kind of a half proof. I'm going to show this to my wife. My wife is a mathematician, a very good mathematician, and we're not going to show my wife however we do math. That's going to be our little secret. She won't like my proof because I'm just going to ignore part of it. I'm going to basically state something as being given because this is why I can't really be a mathematician because I don't have patience with certain things. But then I'm going to the rest of it will follow. Okay, so the third one. Okay, the eigenfunctions. Okay, of a Hermitian operator. Form a basis. Okay, so first of all, we have the word basis, and we have to understand what that means. And this one here is used for almost every single thing in campus. So what is a basis? Okay, so basis is going to be if some set of quantities form a basis, then any arbitrary function, okay, whatever that means, actually it can be a more general thing than function, okay, can be written as a linear combination of these of the set of functions, of the set of quantities. Let me give you an example that you actually already know. You actually know from general physics, you also know from Calc 3, you just never thought about it. An example of this is I, J, and K, the unit vectors. When they form a basis. Okay, because any vector V can be written as a linear combination of them. So, right, I can say this. I can say my vector V is, 5I hat plus 3J hat minus K hat. I'm writing an arbitrary vector. It's a linear combination of these two like that. I, J, and K form a basis. Okay. And even people in my general relativity were making use of that in general relativity because it turns out you can do really remarkably profound things with that statement. So what happens for these to be a basis set? So this right here, these would be the basis sets. This is a basis set. Basis set. In our case, any arbitrary function can be written, any arbitrary function f can be written as some sum on n equals 1 to infinity. However many basis functions there are, often with a lot of these functions, there's going to be an infinite number, except when there isn't. Of a sub n, phi sub n, where O acting on phi n equals lambda n phi n. So these are they're eigenfunction of some operator O, and a sub n is a constant. Okay. That's going to be the heart. That's one of the hearts of quantum mechanics. And we'll see how that's actually going to be the origin of the uncertainty. So I'm not going to do a lot with the uncertainty principle for the simple reason that the only way you can do it at this level is stupid. And so I'll give you basically the theoretical basis for it, but as far as making it rigorous, I'm not going to do this. Because if you're looking at the handout I gave you, they'll go over some stuff of it, and it's just stupid. You need a little bit more profound physics to do it properly. So, proof. Okay, to do the proof formally, what would you have to do? And this is, I'm not gonna do it. You would start off with this, and then you'd have to prove that this series, what do series have to do for them to be meaningful? They have to converge. So to do the proof formally, I've set this up and then I prove that this converges. No. To me, why would we do this if it didn't diverge? We wouldn't. It's stupid. Okay, let's write something in terms of something that just equals something. Yeah. Fine. Go and do sociology afterward. This is being recorded, isn't it? Okay, that's good. Oh, no. What do you mean that? Good. Okay, so, obviously, you'd write it like this. So my proof is going to consist of the following. I'm going to assume convergence. Again, this is where my wife would say, you can't do that, she'd be right. I'm going to assume it converges, and the proof will then consist of if we can find values of A, if we can actually come up with a finite expression for A, then we know that we can do this. So we will assume truth. So I'll put this in quotes because it's a hat. Okay. We will assume convergence. Okay. Of the infinite series. And see if we can determine, find a finite, find a well-defined expression for a sub n. If we can do that, then we're going to call it good. Okay. So I think the easiest way to do this is I'm going to basically give you an example here. Suppose I want to find A7. What would A7 correspond to?
N equals 7.
Yeah, so n equals 7. So what would this be? Actually, let's say n. Let's make it 3, so I don't have to write it all the times. So this is saying f equals some constant A1 times phi1 plus A2 phi2 plus A3 phi3 plus A4 phi4 plus all these terms here. I want to find this. Okay, this is going to be the technique. We're going to use orthogonality. Crazy. Okay, so to use orthogonality, what would I do? What does it mean to be orthogonal? So when you use orthogonality. Nicole. Orthogonality means what? Phi n star phi m dx equals 0 if
And
n is not equal. Okay. Here's it. I'm going to multiply both sides by
3.
by 3
Yes.
by 3. It is functionalized by 3 star.
Oh.
So this gives me pi 3 star f equals A1 pi 3 star pi 1 plus A2 pi 3 star pi 2 pi 2. A3 pi 3 star pi 3 plus A4 pi 3 star pi 4. Now what will we do? To properly use orthogonality, our next step has to be
Integrate.
We have to then integrate this one. Then we have to integrate this whole thing here. Whole thing here. Yes. So what do we get? Get this from here, get this integral from minus infinity to infinity. 5 star f dx equals, I can pull out that a1. That gives me this. 5 star 1 dx. It's a2 integral here. 5 star 2 dx plus integral here, multiply 3. Okay. From orthogonality, what does this integral here have to be?
0.
0. Gone. Hey, what does this integral here have to be?
0.
Gone. What does this integral here have to be? Equal. Well, not equal to 0. Now, frequently what we're going to do, we're going to use what are called normalized eigenfunctions, which mean what? But that's going to be
1.
That's going to become 1, but let's say we don't know that yet. This is not equal to 0. This side here is not equal to 0. So what that means here is that this a3 equals the integral from minus infinity to infinity, 5 star f of x, all over the integral from minus infinity to infinity, 5 star 5 dx. This is a well-defined constant. Okay, so I have a well-defined method for finding all these coefficients.
Would I pick any, any?
Hey, let's do that next. I want to find the Arth coefficient. If I want to find the AR value, okay, what does it mean to be the Arth coefficient? R is 1, or it's 2, or it's 3, it's some fixed value. So generalize this. To find AR, where R is fixed. So now let's do the general thing. What do? We multiply both sides by 5 R stars. I can pull that inside here. Mathematician had already bulked that. Actually, sometimes you do have to be careful with that. You can get these weird things that if you make some assumptions, you get that 1 equals 2. Which I like. But mathematicians have a problem with. And often involves arguments like that. So turns out these don't happen here. Okay, then what would we do? Integrate. And use orthogonality. What do we know about all these terms here? There's an even number of terms here. Why is this beautiful? Which is why if you do a push-up every time you use orthogonality, eventually you get one muscles.
Because all of them except for AR.
Yes. Every single one is 0, except when this n equals R. Everything else is 0 because of orthogonality. So the only one that survives is AR. Integral from minus infinity to infinity of phi R star by R dx. This whole thing is set by Arth coefficient. Later on, I'm going to take that term there to be more. But I don't know. We don't get that right. Okay. That's the truth. The fact that I can have a concrete method for finding any of these coefficients. You know, that probably is the first time any of you have seen this argument. But if you take more sophisticated courses in mathematics and physics, you're going to see that argument all the time. That is used everywhere. Okay. Does that make sense? Questions? Okay, now let's actually start doing a real problem in physics with solving these things here. We're going to start with the simplest problem. The simplest problem is going to be one particle in one dimension with some potential v of x. And then once we get this problem solved, we can then go back and I want to then re-examine all these postulates and see them in action. So right now, this is all very abstract and theoretical we've done. Now let's apply these to a real problem that we're going to have over time. So, before we develop the ideas behind postulates and properties of Hermitian operators. Let's solve a simple problem. The problem we're going to define is going to be this. We're going to solve the one particle 1D problem where the particle is moving and a potential energy v of x. Okay. So let's set this up. Hey, you tell me how to get that. What would we have to solve this for? What was postulate 3?
Diagonal.
No. But if you want to find a wave function, how do you find a wave function? Go to the corner market. No, where did you find a wave function?
Right, the classical energy in terms of position. Yeah.
And momentum and
replace these quantities.
with the quantum mechanical operators and then Shazam. Okay. We're gonna the Shazam part we have to work that a little bit. That's gonna be the rest of the lecture today is what does Shazam mean? I can't look at that. So define psi. Use the third postulate. Okay. You're going to say energy equals kinetic plus potential. Okay. What is our T? 1/2 mv squared. And our potential here is only a function of position. Now we can't leave our T like this because we have to write it in terms of, I gotta put a little X here because it's a velocity just an extraction. We just have one dimension. We have to use momentum. So what's our standard trick here? Yeah, we put the top and bottom by mass, and that gives us this px squared over 2m plus vx here. So this is entirely classic. Okay, how do we make it quantum mechanical?
Everybody has.
Party hats. Party's right around the corner. Okay. So what does this go to? I. H bar. Partial with respect to T equals. What does px squared mean?
Yeah, stuff. Yes.
This is px acting on px. Okay, what does px go to?
This I
Minus I h bar,
partial x.
force respect x, and it has to act on minus I h bar, pressure respect x. All over 2m. What does x hat go to? This was x. Okay. Minus I times minus I is just -1, right? How come? Minus is 1. I times I is 1. I times I is I squared, but I is square root of -1. So I squared is -1. Okay, divided by 2m here. So this gives me minus h bar squared over 2m. A derivative acting on a derivative gives me a second derivative. Like this. And this is here. Okay, this whole side here, what do we call this operator on the right side? That is my Master Hamiltonian operator H. That's by definition. So the Hamiltonian operator is always your kinetic energy of the system plus your potential energy of the system. This can get a lot more involved, and it almost always does. This is the Hamiltonian operator. So I'm just going to write this as H, because it's going to be harder. It's going to be easy to write like that. Okay, then this has to act on a wave function. Now, what variables will my wave function depend upon?
T and x.
Yeah, it's going to depend on the position and the time. Okay, I'm going to write my wave function a little bit different from how I've been writing it, just because later on I'm going to have a standard wave function. I'm going to write this wave function as basically a fancy size. It's actually going to be a capital size. So, since the wave function depends on x and t. Okay, write it as. Okay, I'm gonna write a fancy side like this. It's a function of position. I'm writing it like this because eventually I'm just going to write my regular psi bow. We'll see what I'm going to do now. So I'm going to write it like this. Okay. Now, question is, how do we solve this? Okay, so this is going to be probably, for most of you, this will probably be the first time you've seen this technique. I always tell my students there are 4 most important techniques in mathematics and physics. As long as you know this, what are they? Separation of variables, and this is going to be the real separation of variables that I'm talking. Okay, so you're going to see what that actually is. What's the other one? No, 3. Multiplying by 1 in a clever fashion. Adding 0 in a clever fashion. And then scalar extension. Okay. So what we're going to do is separation of variables. And what does this mean? So there's another technique called separation of variables, which is not this technique. This is separation of variables. So don't confuse separation of variables with separation of variables. I mean separation of variables, not separation of variables. And that's just a sterile. That's just a brilliant. So use the method of separation of variables. This means the following. I'm going to write this as 2 functions here. I'm going to say that this is a function only of x times a function only of time. That's the separation. That's what it means to be separation of variables. Hey, this function here of x, how do you think I'm going to write this? which might be where I'm writing my side like this. I'm gonna call this. Yeah, I'm just gonna make this and call it like this. Have no clue what it is. Okay, I wonder why I'm using side for. Can't wait to find out why. Okay, and then this one here, I'm just gonna call capital T, which is a function of time. Okay. Okay. Something you need to explain? Just
No.
Okay. Okay. That makes sense?
So is the fancy side that like?
That's gonna be
size?
it's actually technically not a capital sign. I'm just writing like this. I'm putting a little more.
Is it different than the
Yeah, the
right?
capital sign is actually that. Yeah, I think this.
Is it different than the small one though?
Yeah, the actual the smaller one you can often see like this, or some fonts will have this. I think this one looks. I think it does. The capital one, which you almost never see. The only time you really see capital letters is you might see them in particle physics, which has this is kind of a completely random piece of information. When you do particle physics, you basically you run through the Greek alphabet and the English alphabet completely. Once you run through the English alphabet, and you've run through the Greek alphabet, what alphabet you go to next? Hebrew. Okay, that goes next. Okay, and you usually only get to the first letter of the Hebrew alphabet, which is Aleph. Okay, which looks it looks like that. If you look actually in the font, kind of if you look at a more fancy font, it looks like that. It's it looks a little bit more fancy than that. It's easier to write like that. It's actually it's not their A because basically it's in modern Hebrew it actually doesn't have a pronunciation. The pronunciation often comes from the vowel or E underneath that like this, but that doesn't look like that. It screws up because basically there's a whole series of letters called gutturals in Semitic languages and Hebrew Semitic, and they mess up all of them. Okay, all the rules are fine, and then you get these Semitic these guttural letters, and they screw up everything. Not that they asked me when they came up with the grammar, but it's true. Okay, what do we do with this? We substitute this back into the original equations. Sub into the original equation. Okay, and you're always going to do this with separation of variables. The original equation is this. And I'm going to take that and put it in here. Then something amazing is going to happen. Okay. What does this derivative act on? What does the derivative with respect to time? The time. What happens when it acts on x?
0.
Nothing. So what can I do with the psi of x?
Get rid of it.
I can pull it out.
Mhm.
We're going to write this as IH. Psi of x. Means t. So this is getting kind of a pain to write, so I'm just going to do it. Equals. Now go back to this h. Remember what this h was? Am I off? I'm not. So this h, remember, was this guy here. Okay, what does h depend upon, variable wise?
X.
X. Hey, what happens when it acts on t?
Nothing.
Nothing. So what can I do with the t?
No.
I can pull it out. This h isn't acting on my psi. Okay, so that's the first step. And then the next step, so if I call this 1, I know the next step 2, and it's always these orders that you do. It's always the same for all these. 2. Divide by the original psi. But divide both sides by this. Get the following. By h psi. Partial t with respect to t divided by psi t equals t psi divided by not that at all psi t. Okay. What wonderful thing happens on this side? The size cancels. Can my t cancel? No, because I'm doing this operation on it. What about on my right? T's cancel. Again, the psi cancel because I'm doing this. So this gives me IH over 1 over t, partial t with respect to t, equals H pi here, psi. Because this H is acting on it. Okay. Now, what do you know about this side here? And what do you know about this side here? This side here only depends on time. This side here only depends on x. Now, what do you know about the variables x? And what do you know about the variable x and the variable t? They are mathematically independent variables, right? Okay. X and t are independent. That's the important. Okay, so I could put in any random value of t, and it has to equal any random value of x on this side. So I could say t equals 13. I could say x equals 4,892.4, and they're always equal. I could change this x value here to 13.2 divided by pi. I could put the t here equal, I could say that this is 1,000 raised to the power 4. Okay, and they're always the same. What's the only way for that to be? How can you then have those always be the same? Both of those terms must be, if they're always the same, and this only depends on x, which is independent, and this only depends on t, which is independent. That can only be equal if both terms equal a constant. That's the only way for this to happen. So these two sides, the two sides, can only be if both sides equal constant. So I can say that this term right here equals a constant, and that this side right here equals constant. Let's look at the psi part. I have this guy. That gives me this. Is this given a name? Hey, this operator x on psi. And what happens? We get psi back times a constant. Hey, this is an example of a eigenfunction eigenvalue problem. So C here is 9. The psi is 9. Now, what would that be? We can. What is my H? Remember this H here. This is really my kinetic energy operator. This is my kinetic energy operator. I call that T hat. And here's my V of x. And this is my potential energy operator here, like that. Okay, what is this energy going to? What is that C going to be? It's going to be the energy. So since this is kinetic plus potential, I can psi. Get psi here times some value. The C must be the energy. Let's be the energy eigenvalue. Since H is the kinetic. That's potential. Okay, so I'm going to put that in there. I'm going to call it E. Write this out. What does that look like? That looks just like our old Schrodinger equation, except now what does it not depend upon? Time. So the other one was the non-relativistic one-dimensional time dependent Schrodinger wave equation. This one is what? Time independent Schrodinger wave equation. So this one here, this is the 1D non-relativistic time independent Schrodinger equation. And this is what we're going to be solving for along the entire rest of this course. Okay. And what's going to happen is that when we solve this for the hydrogen atom, these wave functions are going to be the SPDF orbitals. And then this energy here, these are going to be basically the minus 13.6 over n squared. Okay. Now, what happens to the time? T becomes this I H over T, partial T with respect to T, equals C, which equals really E. Let's solve this. How do I solve that equation for capital T?
What are
You've
we,
done this, you could have done this in physics 125, 126. If you solve this in 125, what would you do?
what are we need the subject team?
Yeah, what's the differential
Gonna
equation?
be, it is long,
So you take the dt over here, and then integrate both sides. I'm going to show you everybody did this, but not today. Okay. I'm going to take the IH right to the other side. And then you integrate both sides. Okay. And what's the integral of the left? The ln of t equals. What's the integral of the right?
dt.
Yeah.
Okay.
dt over IH bar plus some constant here. Okay. Makes sense. Now, how can I write a constant?
What's before T?
What?
The
Which one?
the squiggly below
Squiggle.
under that?
The integral?
No,
The
okay.
natural log. And only use natural logs. Do not use artificial logs. They're bad for the environment. There are a lot of chemicals that don't pollute things, and people cough and hack, and it might be good for the environment. So only use natural logs. Don't like plastic logs. No, don't do that. Bad. Okay, here's a nice trick. I can write a constant in terms of another constant. In fact, what I'm going to do is I'm going to write this. Crazy. I'm going to say that this is going to be by definition the log of another constant. What should I call
okay,
it? A. Log of A. I can say that this is going to be the log of capital T minus the log of A equals ET of IH. What do I know about the difference of logs? It's the log of the quotient I exponentiate both sides, so that gives me this. Actually, now we don't normally like that I in the bottom, so I get the side to the top. Multiply top and bottom by I over I. What is I times I?
-1.
Minus. So this is going to be A e to the minus I et for H bar. So what this means here, that when I write this wave function, I can take that and put it into here. Like that. So what do you think I can do to that A then? I'm gonna basically absorb this here and just call that a new side. So absorb A. Ultimately going to become a normalization house. We don't know that yet. And that goes with this. So we're going to have things of this form here. So those of you who have had optics with me, you might start recognizing this. Okay. So what we're going to do, we'll start on Tuesday, is we want to start solving these for simple problems here. So let's look at let's write our V and set up what we're going to do on Tuesday. So on Tuesday, we will solve the Schrodinger equation for in special case of V equaling a constant. Okay. So what we're going to do is we're going to have this guy here. This is a constant. And this is one of the most common differential equations you're going to get in life. I want to talk a lot about how to go about solving this. And for those of you who've had this before in optics, you know exactly what I'm going to talk about. For those of you who haven't, I'll go set this up, although you may have already had it in differential equations. But this is going to be a really, really common differential equation you're going to find all over the place in all forms of science. Okay. And we're about to get really some of the amazing results of quantum mechanics. Okay, have a good day. Enjoy your weekend. You as well. Thank you. Well, I'll still see you in a little bit.